Hello, everyone. Welcome to another Sunday tutoring session, another Q&A. I really can tell that you guys are ready to go asking me your questions. And thank you so much for putting specific questions this time. That helps me understand where the confusion is or what you really need help with. So everyone who's joining or starting to see this, then I do recommend putting an exact question or specific question with numbers and what isn't making sense. So I can absolutely answer that question and they could benefit you from answering the question. So I'm going to start off real quick before we even actually start. One thing that I wanted to announce is we're getting closer and closer to 10,000 subscribers. So I'm so happy about that. Now, if we hit that goal of 10,000 subscribers, I have a little gift for you guys. So once we reach that goal, I will be doing a live 8-hour Q&A where I answer as many chemistry questions as possible during 8 hours, which is a lot. So I ask that you guys share my videos, let your friends and classmates know, that anyone that can really benefit from chemistry tutoring or my videos in general. So share my videos, help me get to 10,000 subscribers, and I absolutely will be doing a live Q&A for 8 hours once we get there. All right, guys, let's go ahead and start off with the first question. So Cami says, "Hi, Melissa, do you have any videos on thermochemistry and enthalpy?" So I have a little bit of thermochemistry. I believe I only have one currently, but I am working on more. It's a specific example called coffee cup calorimetry. So I'll go ahead and put that link in the chat right now. I recommend watching that video. And then Cami, if at any time you have a specific question on thermochemistry or enthalpy, like Hess's law, or something more specific, let me know so I can answer that. But I'm putting the link right now. And Eleanor now states, "Hi, Melissa, could you go over the polarity of molecular compounds? Here's a specific question." Thank you for that. "Which of the following compounds is more polar based on their Lewis structures?" Okay, so with these, we do have to draw out our Lewis structures, of course. But when we're looking at polarity, there are three main factors, okay? So our first main factor is looking at symmetry. So after we've drawn the Lewis structure, I want you to think, okay, is this symmetrical? Meaning, are all the atoms, let's say if we had something like this, okay, where we have chlorine surrounding that carbon central atom and everything is completely symmetrical, right? So this would mean that it is nonpolar. Anytime that we have our Lewis structure that is completely symmetrical, meaning all of the atoms are the same around it, then that makes it nonpolar. However, if I were to add a hydrogen here, which is actually your first question, a hydrogen there, well, it's no longer completely symmetrical. And what I'm really looking at that is I'm looking for something known as a dipole moment. What a dipole is, it's an unequal pull of electrons. So think of it this way. We know that chlorine is negatively charged, right? And then we know that hydrogen is positively charged. Those two are unequal pools of electrons since there are more chlorines, and it's like a tug of war between elements, and they're pulling in that direction where the chlorine is. So since that's no longer symmetrical, since there's that unequal pool of electrons, also known as a dipole, then that makes this polar. So that's one way to look at it. Another thing is identifying your electronegative atoms. So our electronegative atoms, remember, electronegativity has a specific trend where fluorine is the most electronegative, and then we're increasing as we move, across the period and up our column. I just like to think of it as if fluorine is the most electronegative, whatever's closest to fluorine is then electronegative. So chlorine is very electronegative since it is very close. It's actually right below fluorine. And since there's that it's not symmetrical, then I know it's polar. Another thing too is anytime we have some sort of lone pairs on our central atom, like let's say water in this case, that makes it polar. One, because we have oxygen, and that's an electronegative atom compared to hydrogen. Plus, there are lone pairs on the central atom, adding to that unequal pool of electrons. Think of it as you're adding more electrons on the central atom. So kind of consider it as, I really like to look at this visual as a tug of war, where you have hydrogen that's really, really weak, and then oxygen is like this bodybuilder, and we have lone pairs adding to the strength of that bodybuilder, so they're able to pull and win and be polar. So let's keep going with your question though. So now that you understand polarity a bit better, I went ahead and already drew the first Lewis structure. And then I'm going to keep going and draw the other one, though this structure is polar. Let's see which one is the most polar. So the next one is CHBr3. Okay, it's really similar to the one I just drew. However, instead of chlorines, it's bromine. So I'll put carbon in the center, and then I'll put hydrogen below, surrounded by 3 different bromines. Okay, so though that is still polar, how you can pretty much see which one's going to win between those two is looking at the electronegativity. So chlorine is more electronegative than bromine because it's closer to fluorine. So I know so far this one is more polar and this one's a little bit less polar. And then I'll keep going with the other structures. So the next one, what was it? CH3OH. And for this next one, it's really, really similar. I'm still going to leave carbon in the center. It will be surrounded by 3 different hydrogens. And how I knew that, a lot of times these structures are laid out or drawn how they want you to draw it. So since carbon has to be attached to the 3 hydrogens, I know then carbon also has to be attached to oxygen. And then that oxygen has to be attached to that hydrogen at the end. One more little thing here, I'm going to add my lone pairs. For oxygen, and this is what our structure would have been. Now this is polar due to that unequal pool of electrons, and then so far I'm going to leave that one and then draw the last one just to see which one would be the most polar out of all of them. But I am looking at which one has the most electronegative atoms. And then the last one was CH3 parentheses 2 and then oxygen. Okay, so since there are 2 CH3s, I know that those are going to be on the opposite sides, and then the central atom must be oxygen because there's only one of them. So oxygen's in the center, surrounded by 2 different CH3s. And then we'll see what we got. Okay, so what I would have said, just looking at, because you're just arranging it, which one's the most more polar? Well, I'm going to look at the one that has the most electronegative atoms. So everything here is polar. However, the one that's going to win is not this one because we only have 1 electronegative atom. Same goes with this other oxygen one. There's only 1 oxygen. And then it comes down to these 2. And we mentioned that chlorine is closest to fluorine. So this is the best one. It's the most polar. That's how you would look at it. Okay. And then Taya says, how do you go about adding the dots on the Lewis structure? So how I do that here. Let's actually do this one. So let's do CH3OH. First thing you want to do, I know I kind of just went through this one, but if you're actually drawing the Lewis structure, write how many valence electrons in total you have of this compound. So I'll start there. So carbon has 4 valence electrons. Hydrogen only has 1. However, we have 3 plus this other one. So there are 4. I'll multiply that by 4. We'll get 4. And then oxygen has 6 valence electrons. What I'm going to do next is just add all of these values together. And then this would have given us what 6 plus 4 is 10. 10 plus 4 is 14. So 14 valence electrons. Next, if you have carbon in your compound, you know that has to be your central atom. So I know carbon must be there. And then as I mentioned, they typically draw this the way they want you to structure it. So hydrogen will be surrounding that carbon. And then the only other atom that is possible to also be a central atom is oxygen, because hydrogen only has 1 valence electron, meaning it could only make 1 bond. So I'll put a bond between oxygen. And then now let's just double check. Do we have the complete 14 electrons that we said initially? And we'll note that we don't, because here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. We're missing 4 to get that 14. So that's where I knew the only place that I can put this is on oxygen because oxygen wants to have that full octet. What a full octet means is that there are 8 valence electrons on that atom. So I'll put 1, 2, 3, 4, or I can actually put it on the bottom. And there, that's how I found those lone pairs on that oxygen. All right, let's move on to another question. Savin says, "Hi, Melissa, do you know what is the concentration of a solution that contains," and you're giving me it. All right. So with concentration, what concentration relates to, it's molarity. All right. So this is actually asking what is the molarity of, and we're given 5 grams of barium. So barium has a 2+ charge, and then hydroxide is OH minus, and then let's just balance it out. So balancing our charges, there's this 2 would come down. It would be BaOH and a 2 subscript. So we really have 5 grams of this. And then next, our volume is also provided. So our volume is 400.0 milliliters of our solution. All right. So let's go over how to find molarity and what the formula is overall. So molarity is represented with a capital M. And then beware of that, a small m or lowercase m can relate to either mass or molality. Why do they got to do that? I didn't make up chemistry, right? But capital M is just molarity. So next on top would be the moles, and then divided by the liters of our solution. All right, so we have the volume of our solution, but that's in milliliters. So we'll have to change that to liters. And then we also have our grams, but we want that in moles. So there's pretty much 3 steps to this question. We're going to start off with converting our grams of barium hydroxide to moles of barium hydroxide. So let's start there. And then how we do this, remember, it's finding the molar mass of barium hydroxide. So we have 5.00 grams of barium hydroxide, and then I'm going to figure out what the molar mass of that is. So let's do that. So barium has let's look at our periodic table. So barium has a mass of 137.33. And then now let's go ahead and look at this real quick. So this 2 is actually going to distribute to the oxygen and the hydrogen. So that means there are 2 oxygens and 2 hydrogens within this compound. So I have to account for that within the molar mass. So oxygen is going to be its typical mass of 16, however, times that 2. And then hydrogen will also be its typical mass, 1.01 times 2. And then after we figure this out, let's go ahead and add up all of these values and see what we get. So barium's mass, 137.33 plus 32 plus 2.02. So on the bottom, I'm going to put the molar mass of barium hydroxide, which is 171.35 grams of barium hydroxide. And then remember, molar mass is always the grams over 1 mole. So we have 1 mole of barium hydroxide. That's going to be our first step, just to identify how many moles we have in the solution. So now I'll actually divide. So we have 5 divided by this value, 5 divided by, and our moles would be 0.0292. And this is moles of barium hydroxide. So the next step is to convert. I'm going to go back to my formula. We found the moles, right? Check. Next, we want the liters of our solution. So I'm going to go back to the 400 milliliters and convert that to liters. So let's do that now. I'm just converting milliliters to liters. We have 400.0 milliliters of our solution. Converting this to liters, we can use 1,000 milliliters on the bottom per every 1 liter. And let's figure out what that's equal to. Really, there's a trick in math that you can just move over whenever you're dividing by 1,000. You move over the decimal place however many zeros there are. So 1, 2, and 3. So this is 0.40 liters. All right, almost there. So the last step is to plug them all into the molarity formula. So we're just dividing. So remember, our molarity formula is moles divided by our liters. So the moles that we just found was 0.0292 moles of barium hydroxide divided by our volume in liters. And let's see what that molarity would give us. So 0.0292 divided by 0.40. So 0.073. I'm going to put a capital M. That's how you're going to see concentration or molarity. And this is of barium hydroxide. That would be our final answer. All right. And then Molly says, hi, it's me, Molly. Hey, Molly. I'm having trouble understanding dissociation equations and major entities when placed in water. For example, the dissociation or ionization equation when placed in water, and I believe that's ethanol. Okay, so let's put those two together. All right, so we have C2H5OH plus H2O. All right, so when we're looking at this one specifically, it's a little bit of a special case in a way. How I want to look at water is actually rewriting it as HOH, just so we can easily see where everything's going to go, or like where everything's going to switch. So I'm going to start off there specifically with this type of reaction. And essentially what's going to happen is we're actually going to form H2 gas. And how we form that, it's kind of still like that whole inner with the inner trick and outer with the outer trick that I typically teach. And what I mean by that is where this hydrogen and this hydrogen are going to combine. And then, so that's the inner with the inner. And then the outer with the outer are also going to combine. So that is essentially what's happening with this reaction. So here, let's go ahead and rewrite this. So in the middle, that's where we get that H2. And then on the outside, that's where we actually get, I'm going to rewrite this once I put it together. But this is OOH. And how you're really going to see this is it's actually going to look like this, where it's CH3COOH. And then that's going to be plus 2 hydrogens. So that's essentially, and I don't even want to necessarily state this, but this is what we would actually combine to get. There we go. So we would form CH3COOH plus H2 gas. And then let's see if there's anything besides just doing water and, as I mentioned, just doing HOH. That's easier to kind of see the switch around. But let's see if there's anything else with that. So you did talk about dissociation and ionization in water. Now, what I want to look at is, I hope that you actually went over this already, is talking about acids and bases and understanding like how acids are going to donate a hydrogen and how bases are going to accept a hydrogen to form a conjugate base or a conjugate acid. I hope that makes some sense, or you've heard that before, but that's essentially what's happening here. So what's happening with this one, and actually even make sure I put this process right. H2SO. Yeah. I actually feel that you didn't do that just yet, come to think of it. Because you're talking about dissociation, I believe you're just part of the first half of chemistry. Hold on. Let me redo that. You're talking about a combustion reaction here. Sorry about that. You're talking about a combustion reaction here. I'm going to reiterate that. Let's do this a little bit better since you're not in the class that I'm thinking you are. So what we would do here is, this is a type of combustion reaction in a way. It's called an incomplete combustion reaction, where essentially what would actually form here, would be carbon monoxide and then H2 gas. And then if we were to balance this out real quick, this would have been 2, and then this would have been 4 H2s. It's still kind of going off of how everything is then dissociating. H2 is not present in the equation. H2O. Oh, I see. Okay. So you're just stating that how to dissociate just that. Got it. Okay. When placed in water, that makes so much more sense. Okay. This is a liquid, and then we're dissociating this. I see what you're asking. Okay. So that being said, we're still going to form H2. what you're going to do is essentially it's going to be CH3CHO plus H2 here. Then, and how I noticed that essentially was, here, let me see if I can draw this out a little bit better. H and, okay. So this still goes back to when we're placing this in water, how is this going to break apart? Like what's going to combine? Everything's being dissolved, yeah. So when I'm doing that dissolving, though I am still thinking of water per se, what we would look at, I know it's not really shown here, is just what's going to be donated. Oh, how to explain this part? Sorry, I'm thinking of, since you guys haven't gone over acids, I would see it as this, where our this one would have been CH3CHO is technically hidden within this. And it's going to be negatively charged, and then we actually would have an H plus charge. Now I'm missing an H. So I'm just going to account for all my H's for a second. This is 5 and this is 6. Here we have 3 and we only have one more, so 4. So this is a specific reaction that how it's going to break apart. We have gone over strong and weak acids. Thank you. That's helpful. Okay. Then awesome. Then what you're going to be talking about with this is how this is going to dissociate, meaning how is this going to donate a hydrogen? And that's essentially what's happening here. So this is a form of acid. And what's going to form is that we're going to donate a hydrogen. And that's exactly what I'm doing here. So I'm just looking at the conjugate acid and the conjugate base pairs. So what I mean by that is this hydrogen goes away. Okay. And then what's essentially happening is because we don't just want to have an H plus, we want to break that apart more naturally or have it be a better reaction. Then you're also going to take away another hydrogen. And that's where we form that H2. And then you lost a hydrogen from this first part. So that's why I'm forming CH3CHO. So I hope that's making some more sense with that. Really what I'm doing is I'm removing a hydrogen at the end, and that's how I formed CH3CHO. However, I'm not just going to be left with H+. I would have some sort of H2 gas that's still left. That's where I got that H2. So this is a specific type of reaction to show how it's dissociating, but it does follow that kind of acid, like strong acid, weak acid sort of idea where you remove a hydrogen because it's being donated, and then the product side you're going to have one less hydrogen. Okay, so I hope that's making some sense, but this is kind of a more like a specific case to definitely know. I'm going to move on to next question. Abhinaya is stating calculate the speed of light in water, and then we're given n is 1.33. And then the speed of light is 3.00 times 10 to the 8th. And then meters per second. Calculate the speed of light. And then n 1.33. Okay, let me go to my formulas to see what I'm doing. Okay. I believe you're doing Bohr's law. Actually, Bohr's orbital model. Let's see. Okay. I'm going to go back to, sorry, I'm looking at what formula I'm going to use for this specific case since we're looking for the speed of light. Not its frequency, not any of that. Let's look. I'm just saying what else we're given. So you're asked to find, let's see, n is equal to 1.33 moles. I don't see how that would be moles since we're not using moles for that. That's all that's giving you. I'm assuming you're using, I mean, the only thing that you use n for is really Bohr's model. So you usually use this. But the fact that they're giving you speed of light is weird. I would be finding the frequency of it. Isn't it just NC? N over C? Thomas, moles over speed of light. So there's a specific, since you're looking for the speed of light overall, N is equal to C over V. So I think I'm just looking at it as what is your n that you guys are talking about. You guys are talking about wavelength, because that specific formula that you're looking at is wavelength, not n. Maybe it was just difficult to write it that way, but even then you're not looking for n. But here, let me go to my formulas and I'll show you what I'm talking about. So you have three specific formulas. You have frequency, which is equal to the speed of light over your wavelength. You have energy, that's Planck's constant times your frequency. You have energy, which is also equal to Planck's constant times the speed of light times your, or divided by your wavelength. So those are the main ones that you'd look at whenever, that's molar concentration. It's actually not. So the speed of light in water. Let me see what I can find with this specific formula, guys. Maybe we just do it differently where I'm from, but let's see what I can find with this. Let me look at what I can find, what formula I'm probably just missing. One sec, guys. Okay. Because I know there are so many different ways to word questions. So let's see. Maybe I just haven't seen this question yet, but we can figure that out. No, haven't seen it specifically in this format with n. Interesting. Okay. It is n is equal to c over our frequency, which you're just looking for frequency. Interesting. Okay. Good to know that they still have those types of formulas. Personally, in California, at least where the school districts here don't use this, but good to know. So what you're going to do, you are going to use this overall formula. And yes, you actually would just plug it in. Since we are looking for the speed of light, or really our v, in this case on the bottom, what I'm going to do is let's rearrange this formula so we can solve for v. So I'm going to multiply both sides by v. And then from here, our v's would cancel. And this is our speed of light is equal to v times n. And then lastly, just divide over the n. And then we'll plug in from there since we have all of our given information now that we have the proper formula set up. So our speed of light is then going to be equal to the constant that was provided, 3.00 times 10 to the 8th meters per second. And then divided by that would be 1.33. We'll divide those two values overall. And then let's see what we get. So in this case, 3.00 to the 8th divided by 3.00 to the 8th divided by 1.33. And then we're going to get a larger value. So let's see what we would have gotten. 1, 2, 3, 4, 5, 6, 7, 8. 2.2, I'm going to round 6 times 10 to the 8th meters per second. That would have been our final answer. All right, so that's what we would look at. Interesting. I even figured out a new way that you guys can be asked the question. Cool, thank you. So next, Tuyen says, what wavelength of light in nanometers must be absorbed to promote the electron of lithium 2 plus from n equals 1 to n equals 3? Okay, so this one is one formula that we'll get into. Now that we're talking about finding wavelength, let's find our other formulas for this one too. Okay. And this is, here it is. This is a bigger formula. Here, let me just find it. There it is. Okay. So what I'm going to have, it's going to essentially be 1 over our wavelength is equal to a specific constant that they would have to give you because we're looking for our wavelength. So this would have been 1.0973 roughly times 10 to the 7th meters to the negative first divided by, I'm going to say hc. H is just going to be Planck's constant and c is the speed of light. And this is all multiplied by 1 over n1 squared. So our first n, and then minus 1 over n2 squared. And I'll plug everything in. So this is the formula that we had to know. We're solving for our wavelength, and then we're later going to convert that to nanometers. So all I'm going to do is plug in the values that are provided. So we're given that n is equal to 1, and it's going to n is equal to 3. So n equal to 1 is going to be our first n or orbital. And then from here, energy level really. And then N2 is going to be 3. I'm going to plug everything in. We also know what H and C are. So H is actually equal to 6.626 times 10 to the 34th, I believe, negative. And then we'll plug in those values and also give you the speed of light. Come on. There it is. Negative 34th joules. Let me move this up. Times seconds. And then C is the speed of light, 3.00 times 10 to the 8th meters per second. I'm going to plug in all of these values and then we'll be close to done with this one. So 1 over wavelength is equal to this constant divided by our Planck's constant. So 6.626 times 10 to the negative 34th joules times seconds. And then this will be multiplied by 3.00 times 10 to the 8th. And then meters per second. Next, I'm going to do 1 over, I have to square this bottom part. So N1 was really 1 squared. And then minus 1 over N2 we said was 3. So 3 squared. And then I'm going to do all this math. So what I'm going to start off with doing is just multiplying these two together. And then I'll divide. So let's see what we get. So 6.626 to the negative 34th times 3.0 10 to the 8th. That gives us 1.9878 roughly times 10 to the negative 25th. I'm going to cancel out what I can. So our seconds and our seconds would cancel. And I'm going to keep going from there. And then next, let's see. On top would be 1.0973 times 10 to the 7th meters to the negative 1st. And then I'll still do this portion. I'm actually going to change this to, instead of 1 squared, it's really just 1 divided by 9 because that's what 3 squared is. And then I'll divide these two values. So 1.0973 10 to the 7th divided by 1.987 to the negative 25th. This gives us 5.520 times 10 to the 31st. We are going to get this in meters. And then next, this is really going to be 1 minus 1/9. So let's do that math. And then I'm going to multiply whatever I got from here, which was something like this, times this value. So let's see what that gives us. I'm almost done here. Okay. This is still equal to 1 over the wavelength. So this is 4.91 times 10 to the 31st meters. And then from here, what's going to essentially happen is I have to flip it. So all I have to do to figure out what the wavelength is, there's two ways you can do this. You can cross multiply where this is 1, and then I'd multiply those two together. So 1 is equal to 4.91 times 10 to the 31st meters times our wavelength. And then I'll just divide over that 4.91 times 10 to the 31st on either side. So that's what I meant by flip it. And then that'll finally give us our meters, and then we'll convert that to nanometers and be done with this question. Okay, so then those two divided would have been 2.04 times 10 to the negative 32. And then from here, this is meters. So I'm going to convert this to nanometers because that's what the question wanted. Now with nanometers, all I have to do is know that 1 nanometer is equal to 10 to the negative 9th meters, and then the meters and meters would cancel. I'll divide by that 10 to the negative 9th. Let's see what we get, 2.04, negative 32 divided by 10 to the negative 9th. Okay, wavelength would have given us 2.04 times 10 to the negative 23rd nanometers. That's it. So it was knowing what formula to plug into and how to use the formula. Next question. I'm going to go over Evelyn's question. Evelyn asked, can you go over organic Lewis structures? Sure. Evelyn, is there like a specific question that you are talking about? I'm just going to roll with it. So let's see what I can come up with organic Lewis structures. So I'm assuming you're talking about, like, let's say if I were to, and by the way, when we're looking at organic Lewis structures, they're typically known as alkanes, or here, do a quick little lesson on that. As alkanes, really, I'm just looking at something known as a hydrocarbon. What this means is that we're going to have carbon and hydrogen together, and I can have something a little bit longer. An alkane is also, think of it as a carbon chain that only has single bonds. So if I were to draw the structural way, so the Lewis structure way, and then I'll show you how to actually do the skeletal way. So now looking at, let's say, let me give you an example. So let's do CH3, CH2, CH2, and let's do CH3. Okay, something like this, something a little bit larger. So what I'm going to do is, luckily with these types of organic Lewis structures, it's already written in the format that they want you to actually draw the structure. So let's look at that CH3 at the end. Now this goes back to knowing your valence electrons, knowing, or even really what this looks like, the fact that carbon can make 4 different bonds since it has 4 valence electrons. So I'm going to surround this by 3 different hydrogens. And then I'll link this to the other carbon that we have next. So this is going to keep going. And then I'll show, okay, well, this is carbon and that's attached to 2 other hydrogens. So then that's going to attach to 2 other hydrogens, and it's going to keep going in the same sort of manner, same sort of pattern, where this connects to the other carbon, and then on top are the other hydrogens. And lastly, it's going to end with that CH3 group. It's also known as a methyl group, which you're going to find very quickly in organic chemistry, where this is still surrounded by 3 different hydrogens. So that's how you would overall draw the structure of something that's an organic Lewis structure. I'm assuming that's what your question was. Let me know if anything else. But that's how you would draw your structure overall, kind of just going one by one. And it's already kind of written in the way that they want you to draw it. So yeah. All right, I'm going to move on. So Jose, I'm going to answer one of your questions, just because I do want to give a chance to, everyone else to at least have one of their questions answered. So I'll start off with the first one, or if you have a specific question that you really want answered, let me know. But I'll start off with the first one, and I will move on. I can only answer one at a time right now. So Jose puts C2, this chemical equation that we're given that's balanced, and let's see what we're doing with it. So 2CO2 plus 3 waters. Okay. H2O. Okay. Calculate the standard molar enthalpy for the complete combustion of liquid ethanol using the standard enthalpies formation. Okay, so we're looking for delta H. Got it. And then we're doing standard enthalpies. Let me pull up my table. So standard molar enthalpies is essentially looking at what the individual enthalpy of each compound that we have that we're given. So what I'm going to do right now is I'm actually going to pull up a table with the enthalpy, the standard here. I'm going to look that up because they typically give you a table, by the way, for the standard enthalpies, or they tell you to look in the back of your book of formation. Yes. So I'm going to look at a chart with that while I do this, and then I'll give you the formula as I'm looking for that. All right. Let's see if I can find it real quick. And then I'll write down the formula that you need to know for this specific type of question. So let's see, where is this? Okay, sorry guys, just looking for here it is. Perfect. Okay, so when we're doing this, the formulas that we want to look at, and even before looking at all of this, I'm just going to focus on what am I doing really? So our enthalpy is essentially talking about our heat transfer. Okay, so that's defined as delta, or the triangle H. So this is going to be specifically of our, I'm going to say RxN, that just means reaction. And there's a specific formula that we want to use where this is going to equal the sum of, I'm going to say N, just meaning the numbers or coefficients in front, like that 3, 2, and 3, times your change in enthalpy of formation of your products. I'll explain what this formula means. And then minus the change, or actually the sum times, again, the moles or whatever coefficient we have in front of our change in enthalpy, again, of formation of our reactants. So this is the main formula to definitely know. Definitely jot that down. This is going to help us figure out this question. And what I'm going to do next is pretty much plug this all in. So how I'm going to rewrite this, I'm going to focus on just the products for now. So the products for now are our water and our CO2. So starting this off, I'm going to put it in brackets where I do have to put the coefficient in front. So where I'm taking these coefficients is the 2 here and this 3. Okay, those are the ones I'm going to be using. So we have a 2 times our, I'm just going to put our enthalpy of CO2. Then we're adding this all together. So I'm going to say plus 3, because that was that coefficient, 3 times our enthalpy of H2O. And this is specifically of our products. And then, as I mentioned, you'll actually get a table, which I'll give you the numbers as to what they are. And then I'm going to keep that together. This is then all subtracted by the reactants that are provided. So minus the change, and I'm actually put a bracket again, the change in enthalpy of ethanol, so C2H5OH. And then this is plus, we had a 3 in front of that O2, so right here. And then that's what I'm also going to place. So plus 3 times our change in enthalpy of O2. So this is the general form as to how you're going to find the overall enthalpy of your reaction, which is what this question is asking. So what I'll do is actually plug in the values. Let me go over the chart. So the chart, we have CO2 in its gas form is actually negative 393.5. And then I'm going to multiply that by 2, just putting in all the values. For liquid water, it is negative 285.8. And then still bringing down that 3 in front. I'm going to keep this in brackets. Minus, and let me actually find this one. For ethanol, looking at, there it is. So for ethanol, it's going to be negative 277.6. And then plus 3 times, I have to find O2s. So O2 would have been, I believe that's 0. Let me find that. There's a huge chart that I'm looking at. So give me one sec. Let me see if mine actually has it. It does. Yeah, it is 0. Okay, so 0 would have been the case for O2. It's typically anything that's diatomic, like O2 and H2 would have 0. Okay, so now that I use those values, I'm just going to add everything together and we're done. That's all you have to do. It's really just knowing what the formula is, how to use the formula, and remember there is a chart that's actually called standard enthalpies of formation. Okay, so that's something that you'll see. So 2 times negative 393.5 plus 3 times negative 285.8. That'll be negative 1,644.4. That's what this part is. And then now minus, I'm going to do the other portion, which really would have just been a negative 277.6. These two would form a plus. So I'll add those two together, technically still subtracting. So 1,644.4 plus 277.6. And then our final answer would be, this is our change in enthalpy of our reaction, would have been negative 1,366.8 kilojoules. Okay, and it's still really per mole. That would have been our final answer. As mentioned, it's really just knowing this formula. Okay, knowing this formula, knowing how to use it. And then told my, oh, Jose says, thanks so much. Told my chem class about your channel. Thank you so much. I really, really appreciate that. Really, that helps out so much. Thank you, Jose. And I'm doing the next question. Okay. Determine, so Nelly Gonzalez states, determine the OH of a pH of a 9.22 solution. Okay, so for this, we're given our pH is equal to 9.22. Now, there's specific formulas to figure out what your OH concentration is. And what I'm going to do first is the first formula is going to allow us to figure out our pOH. So that formula is pH plus pOH is equal to 14. So I'm going to do that first, where I'm going to plug in what we're given. So plugging in that pH, and then I'll solve for pOH. So plugging in 9.22 plus pOH is equal to 14. Next, I'm going to subtract over this value of 9.22, and we'll see what we get. So these cancel. So 14 minus 9.22. And then pOH is going to equal 4.78. Now that we have our pOH, we can find our OH concentration by our second formula. So to find your OH concentration, that it's going to equal really 10 to the negative pOH. So all I have to do now is plug in this pOH value, and it's going to be 10 raised to that negative pOH. So this would have been OH minus is equal to, and where this is on your calculator, it's technically going to be a second log. Okay, so just be aware of that. So second log was what you would put on your calculator. Then you'd put in the parentheses negative 4.78. Okay, and then that would give us a concentration of 1.66 times 10 to the negative fifth, since this is a concentration that's measured in capital M or molarity. Okay, so that's it. That's what we would look at. It's a 5. That's all you would do is just knowing these two formulas. Okay. And let's see. B states, can you please do a problem where you place the following in increasing order of least to greatest boiling points? Okay. And your final is tomorrow. Okay, yeah. Let's get this one done then. So we're doing this in increasing order. So yes, that is least to greatest. And then we're looking at boiling points. Okay, so this has to do with intermolecular forces. So what we're going to do first is identify, what I like to do personally is actually draw the structure and then identify what each intermolecular force is, then determine which one is the strongest, and then rearrange everything. So that's what we'll do here. So we have F2, Cl2, FCl, and then CH4. And then CH2F2 and water. Okay. And then Sarah says, for this question, couldn't you use table S to find the boiling points? I wish. I wish they gave you that on the test, but sadly they won't give you that on the exam. So for this type of question, what they're actually asking is for you to figure out the intermolecular force and then figure it out that way. They will not provide you with the boiling points. At least most professors do not. Yeah. So I wish that is another way. It'd be great, but they're not going to put that on the exam, sadly. This is greatest. Okay. So let's go ahead and draw this out. So F2. That one is really just going to be as it seems. These two are just linked together with their lone pairs together. And then from here, Cl2 is going to be Cl and Cl. And then again, those two are just linked together. So exactly what they seem like. And then next with fluorine and chlorine, same concept here. This is still going to be F and Cl. So those will still have pretty much the same thing here. And then next, I'm going to do the same concept with CH4, where carbon is our central atom surrounded by our hydrogens. So there's that format. Next, I see a trend here. So next, this would have been CH2F2. Here, let me draw that here. Where carbon is still our central atom, and then it's surrounded by 2 fluorines and 2 hydrogens. So it could look something like this. And then lastly, water is one to definitely know for Lewis structures and really for anything, where oxygen is going to be our central atom, and this is going to be bent because there are lone pairs on that central atom of oxygen. Okay, so now that we have all this, what we want to do is let's just start identifying what we have. So when we're looking back at intermolecular forces, essentially we're looking at, is this London dispersion? Is this hydrogen bonding? Is this is this dipole-dipole, right? You know, so that's essentially what you're going to look at first. So if something is nonpolar, then that means it's going to be London dispersion. Okay, so anytime there's something that is nonpolar, it's London dispersion. Anytime we have a molecule or compound that is polar, it's dipole-dipole. And then I'll go back to what hydrogen bonding was in a second. But okay, so essentially, and let's go over this one. This is nonpolar because they are completely equal, right? We're still looking at that equal or unequal pool of electrons. So if we have an unequal pool of electrons, meaning they're two different atoms, then one wins the tug of war, or really think of it as one element kind of pulls the electrons in its favor. So in this case, since they are both the same atom, no one's going to win. It's going to be nonpolar. Anytime something is nonpolar, then it is the weakest of all. It's London dispersion. Okay, and we're going to see the same thing for the next one. This one is also two of the same atoms. So once again, this is nonpolar. I'm going to put LD just stating London dispersion. Okay, that's also London dispersion. Now with the next question, these are not symmetrical. They're not the same atom. One indeed would win that tug of war. And which one would win? The most electronegative atom, which we know is fluorine. So fluorine is our most electronegative atom, meaning it would win that tug of war, or meaning it would pull those electrons in its favor, making this polar. And then if it's polar, that means it's dipole-dipole. Okay, so far now we're doing something a little bit different. And then the next one, though, is completely symmetrical. So once again, this is nonpolar, making it London dispersion, or I'm just going to put LD. All right. Next, this next one can be drawn two different ways. So you can draw it where it seems symmetrical. However, that would have not been the case. What we're looking at is does this have the possibility of being polar? Which, yes, it does, due to the fact that these fluorines are essentially pulling in one direction, or in the, or favoring that side. So this would be polar, making it dipole. And then lastly, water is a good one to know. Okay, I see this question all the time, where this is hydrogen bonding, because remember, hydrogen bonding is whenever we're bonding anytime hydrogen is directly bonded to oxygen, to fluorine, or to nitrogen. All right, so those are the main ones that we want to look at. So here we do have hydrogen bonding. So far, this is the strongest of all of them. Okay. So what I'm going to do, since we're trying to go from the least to the greatest, I at least know what the greatest is. The greatest is hydrogen bonding. And let's just go over real quick the order of all of this, right? Where the strongest is always going to be, in this case, hydrogen bonding. The next one is going to be dipole-dipole. I'm just going to put dipole. And then the third one is going to be London dispersion. That's the weakest of the bunch. Okay. So since I know hydrogen bonding is, I'm going to say, the strongest or the greatest, then I'm going to try to figure out what would be the weakest. So the weakest we said was London dispersion. However, we have three of them. So since there are three of them, they're all tied, right? But what we're going to look at to do the tiebreaker is the molar mass of each compound. So if we were to calculate the molar mass of each, what we're looking for is we're looking at the one that has the least or the smallest molar mass. The one that has the smallest molar mass is going to be the weakest. Think of it this way. Essentially, we're looking at boiling points as which one is if it's going to have a low boiling point, it's going to be easier to break. Okay, so if it's easier to break, it has a lower boiling point. If it's harder to break, it has a higher boiling point. So that's essentially the concept here. So with, let's go ahead and just start off figuring out our molar masses, and then we'll go from there. So this is F2, so 19 times 2. This would have been a molar mass of 38 grams per mole. Chlorine would have been 70.9 grams per mole. This is polar. I'm not going to use that one. But next, for our CH4 one, that would have been 12.01 plus 4.04, so 16.05. So once again, we're looking for the lowest, or really, yeah, the lowest molar mass. So this is going to be our weakest so far. And then I'm going to keep rearranging those, just looking at Lennon dispersion, since that category is the weakest. So far, our weakest is that CH4. Okay. And then next, this is going to be F2, actually, yeah, F2, because that is the middle one. And then next, the larger one would have been Cl2. Okay. So far, those are the least or the weakest ones. And then I'm going to now get to our next ones. So the next one is going to be dipole-dipole. We have two dipole-dipoles. Okay. And essentially what I'm going to look at with this is which one's going to be harder to break, meaning which one is going to be even heavier, and looking at that too. I don't necessarily actually want to say that which one's heavier. That's specifically Lennon dispersion. I'm looking at which one has the highest electronegativity, or the highest dipole-dipole. And the one that would have that is the one with the greatest difference. So fluorine and chlorine are really close in electronegativity. So it's not as polar as, let's say, this compound, okay? Because hydrogen is not really electronegative and fluorine is, and plus there's two of them, then that makes this one a lot stronger, okay? That makes this one a lot stronger and more polar. So the next one that's going to go in this, little sequence is going to be FCl. FCl. So FCl, and then after that, we would have, CH2F2, and lastly, we said our greatest one was water. So that's how we order everything. If you need any more help with this question, or maybe another practice problem with intermolecular forces, I do have a video on it. I definitely recommend checking that out for anyone who's struggling with intermolecular forces. Definitely check out, I do have a video called Intermolecular Forces where I go over every single type, different examples, and I also do something very similar like this question, arranging different molecules in increasing order. All right, guys, so thank you so much for being here. I truly, truly appreciate you guys, being here, asking your questions, sharing my videos. That's something that I really value, and I'm really, really thankful for. Personally, my mission is to help as many students as possible pass chemistry. Why? Because I wish that I had someone guiding me when I was in school. I went through a lot when I was in college where most people told me to give up, and that includes my professors and counselors. They didn't see the potential in me that I wish someone had seen. And personally, I see the potential in all of you guys. So I want you guys to see and find your true potential. That's why I do what I do. And that's why I love teaching. So that's a little bit about me. That's why I do these Sunday Q&As and YouTube in general. But thank you seriously so much for sharing and sharing my videos. And I ask that you guys keep sharing, keep telling your friends, telling anyone that can benefit from chemistry tutoring and my videos, so we can get to that 10,000 subscriber goal, and so I can do an 8-hour live Q&A. So that is something. And then I would also love to know, for those of you who are taking your chemistry finals very soon, I want to know if you passed chemistry. I love hearing what you guys are doing next, and how it went. So and what what career goals, what schools you got into, all of that. It's just awesome to hear all of these stories. So definitely let me know, whether in a comment or whatnot, or in a live chat. But yeah, thank you so much for being here, guys, and I will see you again at the same time next Sunday. Have a great day.